Hello everyone, my name is Philip Adler and I'm here to talk today about design code check engine in Allplan Bridge, specifically a verification example which we have prepared for you according to the Eurocode. A little bit about the agenda that we hear today. There will be four main parts. The first one being the introduction to the example itself, explaining how it looks like, guard loads, and schedule. Then we will go through three main parts of this presentation, which is a little bit of discussion about the linear elastic stress calculation, reinforcement design, and code check of the section. So let's get right into it and introduce our example, which is actually a really simple pedestrian bridge. It's a simple span beam of the span of 30 meters. And you can see that it's a simple T-hinged girder bridge with two cornices, and both depths and flanges are hinged. The structural height of the section is 1 meter, and as you can see on this slide, the layout of the pre-stressing is a little bit split at the ends due to the anchorage spaces, so that's how we do it in real-life projects. And in the midspan, it's really aligned in one line of 5 tendons of Y1860-S7, 15.7 millimeter tendons. Regarding the loads, let's firstly speak about the permanent loads. At first, we will consider the self-weight of the section of the main girder. We won't go as much into the verification of the load itself, although it's being a part of the document, which also we prepared next to this webinar. But they can be verified that on this simple span beam, also the loads and the results of the internal forces are compliant with this calculation. The second permanent load, which we will consider, is two cornices. They are placed on both sides of the model or of the section, and they are being placed as non-bearing structural parts. Therefore, the actual mass is calculated directly by Allplan Bridge. Later on, as you will see in the construction schedule, we will apply bearings on each cornice, and we will take into account the characteristic load value of 1 kilonewton per meter on each side. We do not consider any impacts or lateral forces, just to have a simple example. On the other hand, for the live loads, we will consider two of them, and as I mentioned, it's a pedestrian bridge, and we consider some post-bollard at the end, so no vehicles are allowed on the bridge. And therefore, we consider only the crowd on the full width of the section or within the cornices, and therefore it results into the uniformly distributed load of 12 kilonewtons per meter of characteristic load. And on the other hand, we'll consider the crowd only on the half width of the load because we want to cover the torsion as well. And the first full width type of load wouldn't consider the torsion. Also, as we are dealing with the concrete and it's also pre-stressed, we will consider the creep, shrinkage, and relaxation functions that are automatically applied by the Allplan Bridge. When we apply all those loads, we also need to speak out the combinations. So we envelope the crowd full and the half width of the section loads to one exclusive or crowd full or crowd half load cases. And then we have used this envelope in the combination table, which you can see right at the bottom of the table. And we also, according to the Eurocode, use for ULS the combination of 6.10. So therefore we end up only with the one. Sorry. Although in real life projects or in your country, you might end up using a combination group of 6.10 and A or B combination type. Also, as you can see, this combination table considers both gamma G factors and psi factors. Therefore, you can see that the crowd is being applied with both gamma G and psi factors for the respective loads. A little bit about the construction schedule. It's a really simple schedule. So we have fresh concrete in the formwork for 21 days. Then we apply the post-engineering. Therefore, the supports at the ends are activated. And then at 28 days, we apply the cornices. At 40 days, the railings. And at 41 days, the construction is complete. And we start the final creep calculations. And therefore, it's also beginning of service, where we applied those two load cases for the crowd, and then just simply calculating the design and check tasks that we will speak about later. So those tasks which I mentioned are the lean stress, which is performed for a characteristic combination, and we will cover both normal and principal stresses. Then we will go through the code design, and we will go for it in the midspan and also about the support. And when we have the reinforcement, or we have already designed it, we can also code check and explain how each specific check is performed. And we will do all of those at the end of the design working life. So the first task which I mentioned was the linear elastic stress calculation, which is code independent actually, so you can run it for any code you want, and the principles I will explain here should be applied for all of them. And the first type that we need to cover is the normal stress calculation. So this is a bread and butter for you. At first, this whole presentation will have on the left side the snippets of the Allplan Bridge report for each specific task. And as you can see, there is always at the top the determination where, when, and for which combination it was performed, some basic things or information about the cross-section and the properties, and the rest will change accordingly. So in this case, the first part that is changed is that we start with the cross-section characteristics. And to explain the numbers, or to verify them, we need to start actually with the materials. So we can take a mean strength of concrete at 28 days, which is according to this specifically selected C40/50 concrete grade, 48 megapascals. And as I mentioned, we are performing the calculations at the end of the design working life, which means for the concrete bridge for 100 years. Also, yeah, it can be 50, can be 70 if your projects allow it. But this beta factor that applies the extrapolation for 100 years multiplies this strength to be 61.2 megapascals. And therefore, we can recalculate the Young elasticity modulus, or this mean modulus, to 37.9 gigapascals, which is not the value that is applied at 28 days. And when we have this value, also you can see it in the report snippet, there is this rounded value to 38 gigapascals. We can recalculate the rebar and the pre-stressing steel by this working coefficient alpha E to the concrete. So we consider 200 megapascals for the mild rebar and 195 gigapascals for the pre-stressing steel. When we have this, we can calculate at first the first cross-sectional characteristic is the concrete area. So the concrete area of the gross section is 1.485 meters squared. I don't believe there is much verification to this. I think it's pretty obvious. But we can verify the rest. So below it, you have this net section concrete area. And we get to this by subtracting the area of the ducts, area of the pre-stressing steel and of the rebars. And of course, the ducts area are 0 because at this time they are not grouted. They are grouted. If they were just before, you will have, I don't know, 2 stages of pre-stressing, and the one is already grouted and one is not really pre-stressed, then it would be subtracted from it. And as you can see, this value from the snippet is corresponding to our hand calculation very nicely. Then we have these transformed characteristics. So we start from these net characteristics, and by this working coefficients, which I explained, alpha E, we add the reinforcement area and the tendons, and we get to the final value of transformed section concrete area. The very similar example or very simple principle is used on the moment of inertia. And as you can see, there is also this Steiner rule applied, so not much of a rocket science here. Then we need to explain a little bit the difference. There is this part of acting internal forces that are coming from the Allplan Bridge that you can actually see. They are coming from the calculation on the gross section. So to calculate the normal stresses that we use, we have 2 options, either to recalculate everything to the gross section or to the transformed center of gravity. And I have selected for my hand calculation the approach recalculating the forces to the transformed section center of gravity. Therefore, as you can see here, there is a difference between the CJY of the cross section and transform section, and the difference is around 13.4 millimeters, which gives you additional bending moment of 95.5 kilonewton meters. And by adding it to the already existing MZ, we will get the final numbers that we can use for well-known equation. So once we apply the distance to the top fibers, second time for the bottom fibers, and we get with these numbers to the values of minus 10.52 megapascals and plus 5.06 megapascals of tension, and it's exactly the values that you can see in the report. So normal stress was easy, and now we can move on to a little bit more mathematical thing, and it's the hand calculation of the principal stresses. So at first, let me maybe briefly explain to you how it is calculated. So at first we start with the unit stresses. They are calculated by the FAM module of Allplan Bridge. So we have here the results of shear stress XY for torsion and XZ for torsion. And for both, we multiply that unit stresses by the torsional moment mx, right, which is 67.5 kilonewton meters. And by that we get the actual the shear stress xy and xz for torsion being 0.175 and minus 0.09 megapascals. Those are the critical values, and then they need to be summed up with the same principle being applied on the result of the shear from the qy and qz. In this case, we are working our example in the midspan, therefore the qy and qz are zeros, and it's making our life much more easier, but in any case you would apply it here. As you can also see on the left side, there is an example of the mesh and the integration points that we use, and the neutral axis at which we will, as you will see, there is this extreme value which we'll verify at the point V1. So therefore, this value is interpolated between, well, in this case, best would be between the 0.6 and 29. And now you can see what I was talking about. So the V1 is at the position of the neutral axis with this extreme value of 0.2 megapascals. And on the right side, there is this corresponding normal stress result. So how do we get there? As I mentioned to you, there is this calculation of shear stresses, which we can now we go with them into this matrix and apply tau xy and tau xz, and we can use that they are equal to tau yx and zx. Of course, in our example, we need to calculate the determinant and determine the eigenvalues, which you can also see this calculation in the paper for this, and these will result into the eigenvalues of lambda 1, lambda 2, and lambda 3 that are always look like this. So the first one being the maximal value in the tangent, because the sigma 1 is always considered as maximal principal tangent, sigma 2 being always principal compression. Therefore, as you can see, 0 minus 0.198 is giving us this 0.198 megapascals of principal tangent. And yes, of course, there is a little bit of difference between this graphical representation, which is much more rounded. But if you go to the results or the table results, there you can see it also for the 4 digits, and you can see that we are really well aligned between the hand calculation and the results of Allplan Bridge. So that's the part for the linear stress calculation. And now we can discuss the reinforcement design a little bit, meaning that the Allplan Bridge is determining how much of reinforcement area needs to be applied per property set when you don't know how much you need, but you predefine the positions which needs to be filled. So there are many design situations that we can cover, and we can go one by one for the isolated effects, and at the end I will explain to you a little bit how the total value or the overall value is performed. So the first one that we will cover is the flexural design, and as you can see, this flexural snippet, it's working like a bill of material, and we will always look here at the total areas per reinforcement set, and here what is critical is 31.1 centimeters squared and 34.6 centimeters squared on the top reinforcement set. So let's get into it. Those were the total values, and now only for a flexure design at a midspan, we need to use 30.1 centimeters squared, which Allplan Bridge performed as iterative calculation. And you have basically two options to either calculate this by the hand, or you can also verify this by running the code check, and you can see that we are right here at the resistance of the section, resulting in we designed so much reinforcement area that it's giving us the utilization of 99.3%, which is a really great achievement. So also you have this stress strain response, so you can see that what's going on in the section. And to explain it further, on the flexural design, it will be much easier. What does Allplan Bridge actually do? When you have a design situation like this here, that you have applied two reinforcement sets on the tensile side, because Allplan Bridge always starts with the determination of the tensile property sets, and just in case they are all filled up, it starts to add the compressive reinforcement. So in this case, the strains or the average strain of the property set of the boundary will determine which property set will be filled as the first. Therefore, it's having the most effective position. And in this case, you could see that the most effective is with the epsilon S1, which is slightly bigger than epsilon S2. Therefore, the design will fill up the the bottom reinforcement set as first, and only when it's filled up to the maximum, then it starts to fill the reinforcement set that it's above. And in this case, we have designed 30.1 centimeters squared, and at the bottom on this picture, you can see that the designed area is corresponding to several numbers of the bars, which have a clear spacing between them on 62 millimeters, and we have plenty of space left if we need it. So we didn't really need the second layer, which we might end up needing in case of reinforced concrete sections. On the other hand, when you do the detailing design in Allplan Bridge, you always need to use it as a parameter for the type of the design situation. So in this case, we are working on flexural plus flexural detailing design. And as you can see, the number that the report tells us is again 30.1 centimeters squared. Why? At the bottom, you can see the equations or the formulas given by the chapter 9.2.1.1 for the minimal tensile reinforcement being applied in the tensile area, and you can see that by the calculation, it tells us we need at least 21.68 centimeters squared, which is the higher of those two equations. But it's actually less demanding, or demand is less than from the flexural load-bearing point of view. Therefore, always the highest value is kept. Therefore, from the flexure, 13.1 centimeters. And the same principle goes if you have multiple designs in more dates or days or times. And also when you then sum it up with shear, with the torsion, and so on. So we can skip the shear verification here because the shear force is actually 0 at the midspan, and there is a torsion a little bit applied, so we can explain it here. And the most of the principle, how it's checked, will be explained at the check part. So at first we need to see that by the standard gives us this condition for the longitudinal reinforcement, where we can let the area of the longitudinal reinforcement only on the left side, and all the rest variables we can put on the right side, and calculate from this torsional moment of 91.1 kilometer meters that we actually require 4.76 centimeters squared that needs to be applied within this let's say dark blue highlighted effective area in torsion. And as I explained, there are two reinforcement sets, one being at the bottom, one being at the top. And one at the bottom, or if we had two longitudinal reinforcement sets at the webs, they will be considered fully and distributed equally. But the reinforcement at the top, it cannot be seen on this picture, but it's running through the whole length, also in the flanges. Therefore, this 4.76 centimeters squared is distributed by the weighted average according to the lengths of the reinforcement sets. So the bottom one is considered fully, and from the top one, only the effective length around these 1.4 meters is considered. And therefore, by this weighted average, the bottom reinforcement set receives 1.65 centimeters squared, and the top one receives 3.11 centimeters squared, but only for this effective length. Therefore, we have distributed this 4.76. But what Allplan Bridge always does is that it considers all the reinforcement sets or all the boundary distributed equally. Therefore, we extrapolate this value that is inside this effective area to the whole length of the top reinforcement set. So we do the ratio of 3.4 meters to this 1.4 meters multiplied by this ASL top effective, and we get into the result of 7.57 centimeters squared. And those are the numbers which you can see here at the top that Allplan Bridge is telling you to apply. When you select the only torsion and detailing option, then the detailing is designing much higher values, and now let's explain why. The detailing is overruling just pure torsional needs. The chapter for the torsional detailing is telling you that you need to have the distances of at least 350 millimeters between the rebars, and therefore we take the whole length of the bottom reinforcement set, which is 740 millimeters. We divide it by this 350 requirement, and we get to 2.1. But you know, when we design 2, it wouldn't be sufficient. Therefore, we need to go to the next whole number, which is 3. The number of the rebars is the number of the distances plus 1. Therefore, we end up with 4 rebars. And by the multiplication of 1 rebar area, we get to the actual area needed for the bottom property set. And just by recalculating the distances to the length, we get to 247 millimeters. I explained why it's not 350, it's due to this rounding reason. And if you see the result of the report, it's 12.6 and 247 millimeters are explained here. On the right side of this slide, there is the same situation just for a top reinforcement set. So we have 3.4 meters resulting into needed 10 distances, therefore, or 10 spacings. Therefore, we need 11 rebars, and therefore the area at the top reinforcement set is 34.56, which you can see here, and also the distance is 340 millimeters, which can be seen here. As I explained, those values overruled the needs of the torsion itself. The next one on the table is the crack control design. So actually this section is not needing any additional crack controlling rebars, because although the section is cracked, as you can see on the response of the section, the actual crack width is 0.156 millimeters, and the exposure classes that are applied on the section needs to have at further decompression check and also the crack width limit of 0.2, and we are still within the limits of the crack width recommendations, so we don't need to design anything. In case it would be needed, it would be applied here by the iterative calculation. When you do the crack control plus detailing, on the other hand, we will design some of it on the tensile area. As you can see, there is this result of 2.4 centimeters squared, and the reason is that we are trying to cover this tensile area according to the 7.3 dot, I think 2 here, or maybe 3. So we have 2 responses here. Let me briefly explain why. Maybe we'll cover it more at the check part. Is that at the first you have the response of the characteristic combination, and therefore you can see that there is this tension in the concrete of 3.3 megapascals, by which we can calculate the coefficient taking into account the stress distribution with the section immediately prior to cracking. And at the bottom, this is the situation of the iteration process where the cracking moment was reached, and the FCT effective is 4.12 megapascals here. And by that, and our section has a height of 1 meter, and also we have the NED as a compressive force. We apply the K1 to 1.5, we get to AC factor of 0.151, which is used, and as you can see, we have designed 2.4 centimeters squared by extracting it from this calculation. So you can see it's optimized up to 99.9% of the utilization. So we went through those basic design situations independently. So I explained why it's 30.1, why it's 1.6, why it's 12.6, and so on. And as you can see, when you run all those checks simultaneously, it's not the summation, and it's not even the highest number that is applied here. Why is the case? Because it's run sequentially. Therefore, at first, the flexure is designed, and that this 30.1 centimeters squared is needed. The detailing is always run as a parameter, so it just compared if it's higher or lower than the required by the load bearing requirements. As you can see, there is no need from the bleeder failure and the shear part, and then you have this torsion and crack width requirements. And you need to know that this torsion is applied on the already existing flexural reinforcement, and you recalculate this torsion. As I explained, it was this 4.56 centimeters squared. It needs to be added, but to already existing flexural reinforcement being applied at the bottom reinforcement set. Therefore, its weight, or the length that it can be filled, is a little bit different. Therefore, not the full 1.6 centimeters squared is considered at the bottom, but a little bit more is added to the top longitudinal reinforcement set. And again, you cannot see that because this detailing part at the top was much more needed. But as a result, you can see that mostly by flexure plus torsion plus crack width was resulting into this 31.1 centimeter squared of the reinforcement area. So this was the design at the midspan, and now let me briefly go through the design about the support and the stationing of 0 meters, where the shear and torsional requirements are much higher, and we can explain these principles on the stirrups. So as you can see, we have also this need for the longitudinal reinforcement, which is designed here. So the first part of the equations are regarding the longitudinal reinforcement. So we can recalculate the increment of the force as a result of the shear to the longitudinal direction. And in the case of theta angle of 45 degrees, it's the same 608.1 kilonewtons. And therefore, this force needs to be covered by the rebars, and we result into the needed 13.05 centimeters squared of the rebars. And again, as I explained in the torsional part, we need to distribute this by the length weighted ratios. But in this case, it's the only thing is that the shear effective area looks a little bit different to the torsion effective area, and we distributed this 13 centimeters squared to this 3.5 and 9.5 centimeters squared. And so those 9.5 centimeters squared needs to be extrapolated up to all those flanges. Therefore, we end up with 16.4 centimeters squared. And those are the results which you can see in the report of Allplan Bridge, meaning for a whole length of the property set. On the other hand, we need to also design the stirrups, and therefore we can do the calculation for the effective area of the area of the stirrup, which is 15.37 centimeters squared per meter. And as I will explain later a little bit in the check part, we need to recalculate it by the inclination of the stirrups, and for one branch being 8.03 centimeters squared per meter, so the one that determines how much you need, and by the division of the area of one diameter. In this case, we have the 60 millimeters diameter of the stirrups. We get to the spacing that is designed to 250 millimeters, which, as you can see, is also explained here. So this value of ASW is always per one branch. When you do the shear plus detailing, I won't be covering this longitudinal reinforcement again because there are no needs. But as you can see, the amount of the stirrups were not changed, and the reason is that this shear reinforcement ratio that is required, we have basically that by the standard two equations, one for rho W and rho W minimal, and when we compare them and we get ASW divided by S, we can get this needed reinforcement area being 8.4 centimeters squared per meter. And as I explained, that I will explain later, we have two branches effective in the shear, therefore I need to divide this by 2 and result into the need of 4.2 centimeters squared per meter, which results into the spacing of 712 millimeters. And as you can see, it's less than the one needed purely by the shear, therefore this higher value is kept again. The next one is this section table, because I have already explained how the torsion is applied, although this time it would be twice as much almost, because we have twice as high torsion moment. But in this case, it's a simple span beam. We don't have any requirements whatsoever for the flexure, for brittle failure, and for crack width. But in this case, we had some requirements for shear, torsion, and crack width with detailing. I have explained those numbers before, and in this case, let's look here on the right side. We need something from the shear. I explained that shear plus detailing needs 10.03, although actually it would be this 4 point something. If we apply only torsion, we will end up with 2.75, and torsion plus detailing 3.72, and the highest one was 8.03 centimeters squared per meter needed. And this is the end value that the Allplan Bridge could design about the supports. So I believe that that's all for the design, how it looks like, how it's performed, and we can move to the last part of the presentation, which is the more detailed explanation of all the calculations considered inside the code checks. And it means that for already existing structures where you know the amount of the reinforcement area, or you let the Allplan Bridge determine it, you can perform the checks, which tells you that the structure is within the code limits, that the utilization is below 100%. So in this case, the example was tuned that no design was performed, but we applied only the bottom reinforcement set with 37.7 centimeters squared of reinforcement area, and it will be the same in all design situations. So the first design situation is the flexure, or say bending. So the flexure capacity snippet on the left side has several parts, and the first part that I want to explain is the stress-strain response of the section for acting internal forces N, My, Mz. And as you can see at the top, this is the direct response, or the strain and stress distribution and the depth of the neutral axis for the internal forces that you applied. It doesn't mean they are at the resistance. It can happen, but usually is not the case, because you try to be below 100%. And in this case, we are at 96.6%. And if you have a look, there is this stress-strain diagrams per each material. So at first, let me explain the concrete part. As you can see, we use this parabolic rectangular stress-strain relationship. And as you can see on the result of this strain diagram here, at the top in compression, we are at minus 2.19 per mile. And as you can see, we are right next to epsilon C2, resulting into already being at the plastic branch, and this design strength of concrete in compression 22.67 megapascals, which can be seen here. Also, what can be seen here in the picture is that the tensile strains in the concrete are in the omitted for the stress calculation. So the calculation is nonlinear in material considerations. And therefore, all those tensile stresses are recovered by the rebars and the tendons. And as you can see both, they are using these inclined branches, so they don't use these unlimited horizontal branches. And therefore, after the yield stress, it goes upwards. And regarding this 9.9 per mile, it's corresponding to this value of 440.4 megapascals, which can be seen here, and the same 50.68 being here, and 483.9 being applied here, according to those relationships. On the other hand, as you can see, both of them are not reaching the limit, and it can be also seen here that we have still a few percents to go. So what we can do is that you as a user has an option to increase the bending moment up to the design resistance, or as I've done it in a little bit tricky way, but let me show you that if I increase this bending moment up to the flexural resistance RD1 to 100%, it will look like this. And from this 2.19, we have moved to the limit of 3.5 per mile, and you can see that the concrete crushing is governing our situation. Therefore, we are still at the same stress, but we reached the limit here. And regarding this, we can also verify our flexural capacity, because we have a response at the resistance here. So if we draw this free body diagram, then we can simplify it a little bit by assuming this rectangular stress block, considering this lambda value, and up to the center of the gravity of the stress block, we can sum the force in the tendon times the lever arm, force in the rebar times the lever arm, and by calculating we get up to the value of 8,276 kilonewtons, which can be really compared to this result which Allplan Bridge gives us. Why is the difference a little bit here for 23 kilonewtons is that, as I mentioned, I used simplification of this rectangular stress block. Actually, Allplan Bridge considers the real center of gravity of this parabolic rectangular shape of the stress-strain relationships, and therefore use the exact position of the resultant of compressive resultant force. Therefore, the value from Allplan Bridge is more precise. But for our hand calculation and simplified approach, it tells you really that the values are really good aligned. Let me explain a little bit further on a simplified example, which is a little bit different, because regarding flexure, we can also carry out the second order analysis. So on the left side, you can see that we used for this some simple rectangular pier with a length of 10 meters. We considered it as a cantilever. Therefore, the cantilever has a consideration of twice the length of the buckling length. Therefore, in both directions, we have it as 20 meters. And on the right side, you can see that we carry out a really detailed calculation of the whole second order analysis. And at the end is the same old stress-strain response and the check by the interaction diagram. I won't be explaining each independent formula here. Formula here, because I believe that each formula has the numbers and they are self-explainable. But let me just go briefly through some specifics. Every time this calculation is performed, there are actually two runs or two performations of this. First one being carrying out that the imperfections are being applied in the direction of bigger slenderness, and the second one being that it's calculated on the moment resultant. And the one which produces the highest utilization is then printed out in the report. And just by looking at the result right now, I can see that we have applied it in the bigger slenderness method. As you can see, we recalculated the initial eccentricities for y and z direction, and then we apply this geometrical imperfection, and EYZ here is 0 millimeters. It means that we have applied all the eccentricity of the geometrical imperfection in y direction. Therefore, I know that I have applied in the bigger slenderness. You can see it here. It's slender more in the y direction. When these moments are magnified by the geometrical imperfections, we carry out the calculation of the limit slenderness. And at the end, you always compare if the slenderness lambda z, 30.46, is less than lambda limited z. And in this case, it was higher, so we needed to carry out the nominal curvature method, which is currently the only method used by Allplan Bridge to calculate the second-order effects. And this nominal curvature method gives you the magnifying second-order moments, which are then summed with the initial one. And up to those magnifying moments, including second-order effects, the stress-strain response and the interaction diagram is calculated in the same way as Fletcher was. So now why we did also this example was that this is a reinforced concrete section, so it's much easier for us to explain how the interaction diagram is composed, and we can do a hand calculation of it. So let me go for a simplified approach that they usually teach you at the universities with those 6 significant points. And if we start at the top of the interaction diagram, we can say that it's a point 0, which is a pure compression, where, as you can see, the strain in the concrete is epsilon C2, not Cu2, but C2, which is 2 per mile, and it's resulting together with the same strain in the rebars to these minus 35,256 kilonewton-meters of the resistance in the axial force. And as one might know, then the moments coming from the lever arm of both rebars are making it a 0 resistance for a moment. And then we can start moving the inclination of this strain diagram. And when we incline it, we get up to epsilon Cu2 in the concrete in compression, and we get to the neutral axis being at the bottom rebars. And therefore, it's resulting into this situation, which you can see, also the stress distribution. And when you apply it to the formulas, we can calculate the values of NRD1, and yeah, there should be MRD1 as well. Moving to point 2 and 3. Point 2 is the balanced point, maximal moment resistance, where we have reached the yield stress in the rebar, usually the bottom one, and we have reached also epsilon Cu2 in the concrete in compression. And by finding X balanced with the iterative approach, we can come up to minus 16,320 kilonewtons in actual force and 4,900 of the resistance in the moment. Point 3 starts to incline the strain plane of strain. So therefore, the epsilon or the strain in the concrete is not at the limit anymore, and we can find such depth of the neutral axis where it's just a pure bending, meaning that we have a 0 normal force and we have some moment resistance, and you can see NRD3 is 0 and MRD is something, meaning 1,273 kilonewton-meters. Moving to the last 2 points, we move it a little bit more down the road. So at point 4, we have the neutral axis now at the top rebars, and these are the corresponding values. And as you can see, I have simplified it. So the compressive strains and stresses in concrete are omitted because they are small. And at the bottom, no concrete is considered because it's omitted in the tension, and therefore this is the pure tension value. And if we compare the results, which we had just hand calculated, the results provided by Allplan Bridge, it could look like this. Also, this 0.2 is a little bit different because this calculation by Allplan Bridge is already rotating our stress strain plane of stresses because we have applied those imperfections, and it's a little bit out of the plane already by the second orders. Therefore, I will need to adjust my hand calculations a little bit, but still it proves how it works like, and that the calculated results by hand simplified calculations are very well aligned with ours. The next design situation on our plate is the brittle failure. And basically there are two methods that are allowed. First one is determining the reduced pre-stressing area, and if it cannot be found, you need to go to this M representative type of calculation. In this case is this first example, where we can find by the iterative approach this reduced area of the pre-stressing. I can know it also in the report here because it's printed out. And just let me briefly explain what is going on. So when we do the ratio between this reduced and the original value of the pre-stressing area, we need to adjust the pre-stressing primary forces. So those were in the table the original primary pre-stressing forces that can be also seen here. Then we apply this coefficient to them, and we get reduced primary pre-stressing forces, and then we sum those reduced with the external loads, and we come with new adjusted values, total values, which gives us this response for adjusting cracking moment internal forces. And as you can see, this was the response of the original C3 max MZ leading component results, and this is the result with the reduced pre-stressing forces, and for those forces we carry out this interaction diagram utilization calculation again. And just to compare, when you do also this second type of the calculation, there is a little bit difference between the brittle failure interaction diagram and the flexural interaction diagram, because it tells you that in one of those methods, the brittle failure concrete strength uses gamma C accidental, which is smaller than the persistent one, resulting into a much higher concrete strength. They cannot be compared. If you try to compare it, you will see it almost exactly as this picture, that the brittle failure can have much larger resistance. So now we can move to the shear check. So at first, let me just maybe jump a little bit to the theory, because as you can see, that's not our section in the example, but it's an alternative example where I can explain to you how the shear force is distributed to the shear resisting parts and how they are identified. So we have applied, as you can see at the top, a shear force of Vy 80.6 kilonewtons and Vz of minus 5.3 kilonewtons. And the calculation starts at the calculation of shear unit stresses caused by 1 kilonewtons in Qy and Qz. And you can see those distributions here and here. Let me show it on this example of Qz. So relating to tau xz shear unit stress, where we identify the most effective parts of the section, meaning that we show only parts which have, I think, about 80% of the intensity. And when we do that, we can determine the outline of shear effective part. In this case, for Qz, so for a horizontal, and you can see this result here. The same would go for a vertical one, which will result in two separate shear resisting parts, and by their areas, we can do the weighted average, resulting into 40 and 60% of the distribution. Therefore, this shear part number 2 takes 48.3 kilonewtons, and the first one takes 32.3 kilonewtons from this original 80.6 kilonewtons. So when we have explained this principle, we can use our example, because as you can see, I couldn't show you this recalculation when we have only one shear resisting part, because we are only in one plane with one web. Everything is really simple. So I will maybe start to explaining here a little bit that you can have two approaches of reinforcing in Allplan Bridge. The first one being at the top picture, you can draw the boundary representing real geometry of the stirrup. Therefore, you apply number of branches or legs as 1, and when you do the shear calculation, it will be considered as two intersections, resulting into this SW effective of 19.24 centimeters squared per meter. Why is it a little bit different? Because, as you can see, those branches are actually inclined. Therefore, I would have ASW for 2 branches per each branch. So this is calculated for one branch of 10.05, meaning when I have 2 branches, it will be 20.1, right? But as they are inclined, they are not fully effective. And by applying sine function, I get to the effective area of 19.24 centimeters squared. On the other hand, you can also consider this by a simplified, let's say in preliminary stages of your project, by the central line approach, where to cover the almost identical effect, you need to apply 2 branches in the property grid or in the property settings of this reinforcement set. And as you can see, it has a little bit different ASW effective because it's not inclined to the direction of the shear force. And it's, I believe, sufficient for a preliminary project or simplified project. But once you have everything and you are carrying out the detailed calculations, I would go for the first principle. So when we have dealt with the shear effective parts and reinforcement, we can actually go to the actual check itself. So in the direction of the shear force, or in this line, we try to find the minimal width within the tensile area of the section, and at least it's also limited by the last position of the rebars. So in this case, you can see that the BW is here at the bottom reinforcement set, and we can verify it as 0.8313 meters, which is then used in all the calculations. We can also verify the concrete compressive stress at the centroid axis due to actual loading, which is resulting, and also by this limitation, into 4.16 megapascals. And we can also see that we can verify all the results which are coming from Allplan Bridge report. Also, you can see here that we have this Ni1 value being applied due to one of 3 equations. There is this equation AN, BN, and CN. So in this case, I believe it's the AN approach, where the sigma CP is somehow compared to FCD and is resulting, I believe, below 1.25. And all those partial results, which you can see here, are then used to calculate the pure concrete resistance, meaning without shear reinforcement. This value is then compared to the shear force acting, which in this case was 504 kilonewtons. So therefore, only the concrete would be sufficient. Also, there is this minimal one, 805. So we take this one. Then we can calculate how much is resisted by the stirrups. It's 761, so it's actually less than the concrete. And VRD max, it's the resistance of concrete compression strut, which is working as a limit from the above. And at the end, you can see that the utilization is 58%. percent, so it's not that much utilized, but yeah, it's the result of our example. Coming to the torsion, as I have explained at the beginning, there are two approaches to the reinforcement, and it is in this example we used the real geometry, which can be represented actually in the real life project as two types. So you can have in mind the top approach, that is one closed stirrup, that is effective in torsion, or it can also represent the calculation stirrup for this type of longitudinal reinforcement that is forming torsionally effective reinforcement. And there are also two approaches to determine the torsionally effective area, so this equivalent thin walled section. The default method is according to the unit stresses, which I will explain on the next slide. And in this case, for the verification, we have chosen the second type when you switch on the area by the stirrup, which I will explain in more detail. So the default is by unit stresses. Therefore, on the left side, you can see tau xz and tau xy unit stresses from the torsion. And again, as in torsion, we get this, I believe, 80% of intensity, which result into the top right picture if you combine them. And by the intersection of those areas, you end up with the torsionally effective area, which you see at the bottom. And we also identify the center line of the shear flow. On the other hand, this example uses this second approach, and it's formed by the stirrup geometry. And how do we know what is the effective thickness around this? Is that it's told us by the standard that is the minimum value of the area of the section divided by the circumference of the section, or 2 times the distance from the closest fiber up to the center of the longitudinal reinforcement, in our case resulting into 0.175 meters, which you can also see it's written here in our results. One more thing that I need to explain at first is that the TED is not just the torsional moment mx coming as a result of internal forces, but we also consider, in case of a little bit different sections, there is a difference also in this case between the center of gravity and the center of the shear. And if the section is not loaded in the center of the shear, then you need to introduce additional torsional moment. But in this case, the direction of the shear force is going through the center of the shear. Therefore, there is no lever arm, which we describe as delta T. Therefore, there is no additional increment, which can happen in a non-symmetrical section loaded, usually in some biaxial bending. So just to hand calculate and verify, I will hand verify it very easily. I will omit these roundings here and also some inclined things in the center line. But if you do the trapezoidal calculations, you can verify that the circumference is around 3.5 meters and the enclosed area of the center line of torsionally effective area is 0.72, which you can then compare to Allplan Bridge results, and they are very well aligned also with this little bit differences having in mind. To cover the torsional resistance, we also need to explain that the mean tensile strength of the concrete is again extrapolated by this beta CC factor up to 100 years, and I have already explained why it's 4.12 megapascals. Then from this we can recalculate this 5% quantile being 2.88 megapascals, and the torsional torsion is the ULS situation. Therefore, we need to apply the design value, which is divided by the gamma. Sorry, it should be C, 1.92 megapascals of design strength. One more thing, as I explained in the shear or also at the design part of this presentation, we need to consider only the part of the reinforcement that is within the effective length of boundary in the equivalent thin-walled section. Therefore, it's only 1.4 meters from 3.4 meters. Therefore, I consider only 15.52 centimeters squared, together with the reinforcement at the bottom, which is 37.7, which results into the considered 53.22 centimeters squared inside effective for torsion, also having in mind that it needs to be switched on in the input. And as I explained to you, you can see that value here, 53.2. So, I've covered some of those things already in the shear, those first three equations. So we can then form these equations of the torsional resistance purely of concrete, then of the concrete diagonal strut. And then we have two things for the torsional resistance for the rebars. First one being the longitudinal reinforcement and its resistance, which is about 1000 kilonewtons. Newton meters, and the second one being the resistance of the stirrups, and the minimal of those tells you what is the actual resistance of the section. In this case, it would be 665.92. So you can see that the resistance of the stirrups is the limit which you need to play with if the load was higher. And it results into the utilization of 27.4%. When you do flexure, shear, and torsional checks, you can go for the interaction check. So the first one is that we need to cover the stirrup stresses for combined effect of shear and torsion. So the first thing is to calculate the stirrup stress coming from the shear. So as I have explained, you have two branches effective for the shear force. Therefore, I need to divide this VED by 2. And we use theta angle 45 degrees. And we use ASW effective, which results into the shear stress of 156.5 megapascals. The same is applied for a torsion with a little bit different breadth equation, and resulting into the stirrup stress from the torsion around 119 megapascals. And when we combine those two stresses, we need to still be below this design yield stress of the stirrup, which is 435 megapascals, giving us the utilization for the stirrup at 63%. The second part of this check is the combined action of shear and torsion on concrete compression strut, meaning that you combine VED and VRD max plus TED divided by TRD max, and you obviously get up to 14.7% of the utilization. There is not much of a magic here, all the numbers are explained. And as you can see in the report, there is this last part, interaction results for longitudinal reinforcement, which is a result of the increment of longitudinal reinforcement due to shear and torsion. So at first we take the shear force and recalculate the increment to the longitudinal direction. In our case, we use theta angle 45 degrees, therefore it's the same value, but you get it, it's a cotangent function. And for the torsion, it gets recalculated by this one, and you have the forces for longitudinal reinforcement that needs to be additionally added to flexure 1. So you can recalculate this force to, at first, rebars and also to the tendons. Therefore, the increment of epsilon in shear results into 0.12 per mile, and the increment of epsilon or strain from torsion gives you 0.2 per mile. And when you combine those two, you get up to 0.32 per mile, which I can get to the next slide. And this 0.32 per mile is then applied to the response of the flexure. So at the top, this is the response purely of the flexure, And you can see there is this minus 0.2. In this case, it would be around 0.1718. So when you add it to this original, you get up to 0.15 per mile, which you can see happen here, which correspondingly by applying the E 200 gigapascals, you get up to 30 megapascals of the stress, which can be seen here. The same goes for the tendons. So we applied to the original one the increment, and we got up to 6.5, which can be seen here, and it results from 1,204 to 102,067. The next one is being the stress limitation. And as I explained to you already in the calculation of the normal stresses, we use this approach of using the center of gravity of transform section. So I have applied the difference again, an additional bending moment of 71 kilonewtons, and we can verify the normal stresses in top fibers, in compression and in tension, which are very well aligned if we visualize it in this way. But there is a little bit difference to the linear stress calculation. First one being that this is a non-linear calculation. Therefore, as you can see, this 6.84 megapascals in tension wouldn't be covered by the tensile strength of concrete. And you can see that there is this strength of concrete which is exceeded. And therefore, we run these, let's say, fiber state calculations in the whole history for all the vertices of the section, and we remember if the section was cracked or not for the highest possible combination load. Moreover, we cover this also with R sub and R inf coefficients, meaning this lower and upper value of the pre-stressing force, which for the post-tension type of tendons which we have is, I believe, 0.95 and I believe 0.9 and 1.1. And thus, the ordinary primary pre-stressing forces are, again, as I explained in the rate of failure, are adjusted by this coefficient, summed up with external loads, resulting into adjusted total pre-stressing or adjusted total forces that are then used. And as you can see in the results table, there is always this R inf, R sub suffix that tells you which situation caused those different internal forces. And then they are compared to those limits given by the code for a characteristic quasi-permanent combinations. Moreover, you can see that this last one for tendons doesn't have this suffix. It's because the standard tells us that it's compared to the mean tensile stress in the tendons. Therefore, no R inf, R sub is applied here. And as I've been speaking about, you can see there is no tensile branch of concrete here. The last part of each stress limitation report is also the check of anchoring stress or prior to anchoring, which is happening actually independently on the position or the stationing. It's always taking into account the highest value for the tendon which is in the section. In this case, you can see that it's taken from the left part prior anchoring, prior to the losses, and this one is being compared to the limit given by the code, which is compared here, and we end up with the utilization of 94.44%. We are getting to the end. First, crack control. I need to explain a little bit. There was an innovative new approach, which is splitting the concrete section or in the tensile area for the local cracking zones, embedment zones of the rebars and the tendons. And as you can see also in this picture, they can be bundled when they are very close together. And this calculation can be then verified by hand. So let's go for it. At first, we consider, according to the standards, that the middle wire of the tendon is 3% bigger. So we need to recalculate this equivalent wire diameter, which we end up with 9.34 millimeters. Our one tendon area, which we use 7-stranded tendons, is this 10.5 centimeters squared. And the equivalent tendon diameter would be 51.8 millimeters. We can sum this up also with the rebars that we have. So we have 12 rebars, 5 tendons, resulting into the equivalent core diameter of 36.5 millimeters. The bond characteristic between those strands is 0.5, resulting into this zeta1 of 1.035. And the effective depth of both the rebars and tendons that we will use is 0.92 millimeters, which you can see is again the weighted average. Then we can actually start with the usual. So we can, by the head calculation, which is a little bit different to the calculation that is used by Allplan Bridge, which determines it purely by this bond effective amendment zone, is determined as a minimum of those 3 conditions, which gives us in this example 189 millimeters of the effective depth of the tensile area. And at this level, there is this effective width of the section of 918 millimeters, resulting into the area of trapezoid of 0.162 millimeters squared. Then we can recalculate the reinforcement ratio inside this area, which can be, the result can be 0.0567. And then we can recalculate this bond characteristic of both rebars, which as you can see, we have 12 rebars of 20 millimeters diameter, plus 5 tendons with this effective diameter, which we explained before on the previous slide, being 59.8 millimeters, resulting into the K1 being 1.215. We can deal with either bending of the or the pure tension. In this case, we are going for a bending, therefore K2 is 0.5, and the maximal spacing of cracks is therefore, by this equation, 302.2 millimeters. On the other hand, we need to cover the difference of the strains between the concrete and the rebars. And to do that, I need to explain to you a little bit how the KT factor, considering the duration of the loads, is again working as a weighted ratio. Therefore, we need to establish how much is coming from the long term and how much is coming from short term loads. Therefore, I have used this asymptote combination, meaning all the permanent loads and how the response look like. So I have forced this type of combination into the stress or into the code check to show it to you how it's plotted. And you can see that we have 23.49 megapascals in the rebar. When we run this calculation for a C3, we have both short-term and also long-term, meaning variable and permanent parts of the combination, both applied. So the 69.36 is the total value. And by subtracting this from this, I get only the variable part as 45.87 megapascals. And then I can use the weighted average between 0.4 and 0.6 kT, resulting into overall kT of 0.532. And again, I can calculate the effective elastic modulus between the rebars and the tendons which will be applied. And I can finally use the well-known equation where I can use this total stress in the rebar, this weighted KT and so on. And it's, as you can see, also limited. So I believe there is 1 0 missing. So therefore, the actual crack width can be combined from the maximal crack spacing and the difference in the strains, resulting into the overall crack width being 0.0638 millimeters, which gives us the utilization against the exposure classes, resulting into the maximum allowable crack width of 0.2 millimeters to 32%. One thing to mention here is that also regarding the crack control and those exposure classes, we need to verify the decompression check for, I believe, a frequent combination type. And in this case, you can see that the tendons are not lying 100 millimeters inside compression area. But if we did that when we tuned the example, I couldn't be able to show you the crack width calculation itself. So therefore, it goes one against the other. And I have decided to show you that. And in this case, the principle is that this minus sign of the compression distance means that you are on the tensile side. I haven't mentioned it, but those small red arrows, when they appear in the crack control or stress limitation check, it means that the section has been cracked before or is cracked now at those fibers, and it will be considered as cracked, also influencing the cross-sectional characteristics from now on. Last but not least, we can also do the detailing rules check. And as you can see, it's probably the longest report that we have right now because it's considered, it's composed from a lot of different small checks. And we can probably go through them briefly. So the first one is the clear distance between bars in the layer, in the tension. And yeah, the equation is self-explainable. But for what I wanted to talk here about is that it can be represented in your mind either that one reinforcement set represents one layer, or sometimes you want to make a simplified approach and you just model a central line and it can represent two layers. So in this case, we have calculated this 47 millimeters of clear spacing, which is valid for the left situation. In case of the right situation, it will be twice, meaning that the distance between each rebar would be 94 millimeters. Therefore, it's always up to the consideration of the user which approach he used. The second part is the minimum longitudinal tensile reinforcement area covering the flexure. And as I've explained to you, it's always considering also the part, only the tensile part of each boundary if it goes through both compression and the tension. And in this case, you can see that the minimal reinforcement area is sufficient compared to our provided 37.7 centimeters squared, and we get the utilization of 56.5%. Then we have the maximal cross-sectional area of tensile or compression reinforcement with a limit of 4% of the cross-sectional area, and you can see that usually you fulfill this condition. Then we have a shear reinforcement area, which we already covered also in the design of the shear reinforcement, and also we are in the midspan, so it's not that hard to fulfill. And we have explained that this 350 millimeters is needed due to the torsional reasons. In this case, we have this top reinforcement, and you can also see visualized rebars represented, and that we are at 97% of the utilization. What we haven't covered is the maximum longitudinal spacing between shear stirrups, which is limited by the 0.75 times effective depth of the section. And cotangents alpha is always cotangents of 90 degrees because we right now do not consider the inclined stirrups. And on the left side, you can see the visualization is really the longitudinal distance, because as you can use the central line approach, we cannot check the transversal distance between each branches or legs if you want. The same goes not just for the shear effective stirrups, but also for stirrups effective for torsion. There is just a little bit difference that it's also limited by this UK divided by 8, and therefore resulting into the utilization of 37 degrees. There is this, one more remark here is that this U is a little bit different to the UK of the torsional, because once it's the central line and once it's the outer perimeter of the effective cross-sectional area. Then we also check the minimal clear spacing between the ducts. You can see them visualized here, and then we also check them when the grid is in more layers. In this case, it was 150 millimeters, and you can also influence this by the change of, let's say, concrete aggregate size, which is here by default 16 millimeters. And last but not least, is the detailing rules for the crack width reinforcement area, which is going to be explained on the next slide. So at first, we need to get up to this is the response at the cracking moment forces. So by that, we can hand calculate the verification of the effective area in tangent. So it's again a trapezoid. So when you do that, you can compare the results from the Allplan Bridge report, which are really aligned with our value of 0.292 meters squared. And also we need to explain that there is this linear interpolation, because we need the stress at the center of the gravity, I believe, which is minus 3.86 megapascals at the center of the gravity. And this is the value that is used then in Kc, which is coefficient taking into account the stress distribution within its section immediately prior to cracking. Therefore, we are at this cracking moment of 4.12. This calculation, which you can see here, is the case for the wet part of the section. If we have been dealing with the cracks for the flanges, the formula will be a little bit different. And also we have this K1, which is when NED is a compressive force and our height of the section is 1 meter, therefore 1 divided by 1, and it gives us this value of 0.15 of Kc, which is calculated, and from our results we get to 0.148. The K is 0.65 because we have the height of the section above 800 millimeters, because K is the coefficient which allows the effects of non-uniform self-equilibrating stresses. And by this calculation, you get that the minimal reinforcement area is 2.31 centimeters squared compared to our applied 37.7. We get this small utilization of 6%. So that's all from this verification point of view. So I would like to conclude at the end as that I have tried to explain all the numbers that we provide you with, all the principles, how it's applied, how it's composed, and you can always have a look either at this video or at the paper or the documentation which we prepared for this, and or you can always contact us and discuss it. So that's all from my side for today, and have a nice day.